Hello, hello, this is QMG with more quantum computing, the physics of quantum computing to be exact. So, right here, you're looking at the screen of IBM Quantum Experience. Basically, this shows you what is going on in the quantum computer. Okay, right here you can see theoretical results. Right here kind of explains you a little bit of the math going on. But here's the important thing. This is where the qubits are. This is where you put the information. So I'm going to start with one qubit right there. This one says Q0 because we're going to start with a spinning electron. So you can imagine a spinning electron going like this, and you can imagine it's pointing up because it's rotating in a very specific way. If the electron is spinning in the opposite direction, it goes down. Okay, so I'm going to show. So right here you have on the top, all of these are operations, and here's a very interesting one. This is called the Hadamard Gate. So I'm going to put it right there. Now what this one does, this one allows you to put something in a superposition. So as you can see right here, now we got two lines instead of one because it can be 0 or it can be 1. Not both, one or the other. So you can imagine that when you put the Hadamard gate, what you're doing to the electron, you are, in a weird way, splitting it into two parts. Okay, so you can imagine that you have one electron. See, you can imagine one electron going up, spinning in one direction. You can imagine another electron spinning in the opposite direction. And kind of like that. All right, so now which way is a possibility? Well, you can imagine that you have two whirls, right? In one whirl, it goes this way, and in another whirl, it goes this one, but the electron has not decided which way it will be until you do a measurement. Okay, so if you do a measurement, as you can see right here, well, you can actually run an experiment with these quantum computers. I can actually run an experiment and see what happens, right? So if I take just one electron, let me do a measurement. So I pull the measurement meter here, and I guess I'll wait for that one to start working. As you can see, what this one means, it's taking the information from the first line, making a superposition right here where the Hadamard gate is, and then doing a measurement. Now you cannot see clearly here on the screen, but this one looks like a meter, like a gas meter, and it points to the Z. Why the Z? Because the direction of your electrons, either spinning up or down, is in the Z direction. Okay, so this is the Z direction right here. So, okay, up or down is the Z direction. So that's how that is doing the measurement. So when you do the measurement, you either get this one or this one. So in terms of probabilities, what's the probability of getting the first bit is going to be 50%. What's the probability of getting the second bit? The second possibility is 50%, right? So it's 50-50. 50 of getting it up, 50% of getting it down, right? Not something very, I guess, very profound about this one yet, right? And it's not very appealing because we just are using one qubit, one electron, one spinning electron, but it's either one possibility or the other, right? So nothing interesting, but here's something more interesting that you can do. So now let me move. I guess I will erase this one just for the sake of the next one. But so this one is called, so right here, this one is called a superposition state, okay? Up or down is called superposition. Superposition, okay? Right there, superposition. Oops, Superposition. All right. More interesting is when you have something called an entanglement. To create an entanglement, I'm going to put this one right here, connecting. Oh, I need another qubit here. So I need 2 qubits. So now for this one, so with 1 electron, you know, 1 electron is like flipping a coin, right, in the air. It can be heads or tails. We don't know what it is. But now we have a second qubit right here, second line, as you can see. And for this one, I'm gonna connect them with this one right here. Okay, and what that one does, it creates now a superposition, an entanglement with a superposition. Okay, so let me explain this one, what is happening, okay? So initially, so I'm gonna do a little drawing here to explain what's going on. So you started with 0 here, and you put it through an H gate. And what this one gives you is 2 possibilities. This one or this possibility, up or down, right? Well, if we use another qubit and we throw it, and then we use this operation right here, basically what we're doing is taking whatever answer it is here, and that's going to affect the answer for the second one in the following way. If this one is 0, if this one is 0 and this one is 0, it keeps it as a 0. Okay, so that's kind of like these two go together. Or if this one is 1 and this one is 0, it's going to, which it is, right? It's going to switch it to a 1. Okay, so we got 2 possibilities now. Okay, we got a possibility where these 2 right here are 0, and where this one or this one are 1. So the way you write it in quantum mechanics, more standard notation is 0, the possibility 0, 0, or I'm going to put a plus, 1, 1, right? So 2 possibilities, right? Okay, and let's look at what we expect right here. As you can see, we got 0, 0 right there and 1, 1. So what do you think is the probability of one on the other? Well, it's going to be 50-50, right? 50% chance that both of them are heads up, right? Or both of them are tails down, right? And that in itself should be a little strange, right? Because it's kind of like if you throw 2 coins in the air and they always land heads and they always land tails, then, well, you can say there's something weird about those coins, right? Yeah, it's equally weird to see this. I'm going to tell you why. It's not so obvious here, but if you took these 2 spinning electrons and after you entangle them, you let them go and you start separating them. Imagine that you separate them as you move them away, and then you make a measurement. Once they're far, far away from each other, guess what? You still, you will still observe the same thing, okay? So, and remember, this H, split it into 2 parts, one or the other, but not both. So it's kind of like, how do they know how to land even though there is no exchange of communication? There's no exchange of energy and mass between them when they are separated, right? Maybe some energy and mass was used here to set it up, but once they are out of this entanglement, there's nothing here, so it would be weird to see something. It would be weird if you have 2 coins and both of them are heads and both of them are tails, right? No matter how you throw them, okay? Without the exchange of mass or energy. I mean, so this is at the heart of what is weird about quantum mechanics. I mean, why is this happening? Okay. And as you can see, if you run an experiment in this quantum computer, you can actually see what would happen. These are just theoretical results. Again, this is not the actual values. You expect both of them to be 50%, but it's when you run it, actually, you can actually see the numbers that you get there. By the way, you can set this to run it one time or many times, okay? As many as you want, okay? All right, so what happens, so here's another thing. What happens, let me add another qubit right here. So I'm gonna put a plus right there. See if it allows me to get another qubit here. It's running kind of slow. I wonder if, oh, there you go. There's another qubit right there. Yeah, it's running too slow, so I guess somebody must be working on it. What if I entangle three electrons, right? 1, 2, 3 right here. So right here I just have 2. This is called the Bell state, okay? It's kind of like this, like the way I show it right here. Here's the Bell state, okay? 0, 0 plus 1, 1, okay? And of course there is, well, I should put proportional because there are some constants that go in the beginning, so I should put it like that. It's proportional to this. But what if I add another, I entangle a third one, right? So I'm gonna put another entanglement right there. So now we should expect something here. Yeah, there you go. Now we now notice that we have 3 zeros, 3 ones, 3 ups and 3 downs, right? And both of them are 50-50 chance, right? Okay, so that's so basically now you should be, how you write that one formally in quantum mechanics? Well, you write it, so 3 zeros and 3 ones. I'm going to put proportional because there's a proportionality constant that goes around here. So that's the state that we have right here, and that our quantum computer is has available to run. All I have to do is go up here and run the experiment. I don't want to run it right now because I think it's running a little slow for some reason. But here are the theoretical results that we observe, okay? But of course, we can try more complicated things, okay? Here's a state that I actually tried last time. It's a very interesting one. Let me put more gates here. I'll put 1 here. Let me put another gate here. Notice they're all RY gates. Now these gates, and then I put another one right here. Okay, and we're gonna see something really cool. Notice something interesting. Notice that we only have 4 possibilities instead of 8. If you think about it, if you had 3 coins, and heads or tails, if you count the number of possibilities that you can get, the total number of combinations you could get is you could get 8 possible combinations of heads and tails for all 3, right? But notice here we only have 4. Okay, and notice that we have an odd number of downs. So 1 down, 1 down, 1 down, or all 3 down. Okay, no evens downs. Okay, all right. And so this will be interesting as an actual experiment. And by the way, I have not seen this one in any book. So I like to call it the QMG state, okay? QMG state. You can make your own gates and you can call it whatever you want. QMG gate, okay? This is kind of like another state called a GHZ state, okay? This is a very famous state, GHC state. Okay, but this one is a little like that because it allows you to see. This one is more simple, but it allows you to see why quantum mechanics is weird. Okay? Now imagine that 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 I actually take these 3 electrons, I pass them through the Hadamard, I entangle them, and then I pass them through each of these operations. Notice each of those operations is done independently on all 3. And then I separate, and let's imagine that right at this point, I separate all 3 far, far away, so that they cannot communicate in some ways. You put them far away so that there is no time for them to have any communication. Well, we would still expect these results. Immediately, without the exchange of mass or energy. And that's kind of a thinker, right? That's kind of a thinker. And you might say, well, they arrange themselves before they come out. So right here at this point, you can say, well, the three electrons say, you know what? We're going to give these results, okay, whenever we encounter this one. So you could say that the 3 of them have a table of values saying, okay, if this happens, they put all these 3 RY gates, we're going to give these results. But wait a minute, what if far, far away, you decide to change 2 of them? Let's see what happens if we change 2 of them, okay, just to show you. So I'm gonna take, change this one. I'm gonna change this one to an X gate, okay. And I'm gonna put the X gate here. I'm gonna put the X gate here. Let's see what we obtain now. So let's say that we decide to change the gate far, far away. So now notice something interesting, okay? Now we have an even number of downs. So we have 2 downs here, 2 1-1s. We got 2 1-1s here, and 2. You have 1-1 here, 1-1 here, 1-1 here, right? All even numbers or nothing. Okay. All right. So now we have even numbers of downs. So when I had all RYs, they were old odd numbers. Now that I put 1 RY and 2 and an RX and an RX, now I get evens, right? So this is weird. See, if I separate the 3 electrons far, far away, and I change 2 of them all of a sudden far away, randomly 2 of them, I'm going to get these results. So that sort of contradicts the idea that these electrons are conspiring, right? That they arrange themselves, because there's no way, if you think about it, that the electrons can actually do that, right? There is no way the electrons can conspire and say, okay, we're all going to be odd. Oh, we're all going to be even. Because they don't know which ones are going to be changed to Rx. It can be these 2, it can be these 2, it can be these 2, and still you get these results, okay? If you think about it, it would be very hard. Now, if you can figure it out, well, that would be great. I would be happy to hear how that happens. This is, again, similar to the GHC state, but it's a little more simple mine. Okay, but it sort of gets you the idea. If you go into the sides here, you can actually find some work that was done by the IBM people on GHC. It's very complicated, but they actually get it very accurate to the GHC state. But mine, I like mine because it's more simple. It gets to the point, gets to the physics, right? Gets to the, so that's why I like to call it the QMG state. I should write it here, QMG. QMG state. Oh, I named you QMG state for now on. All right, let me see if I can actually run it. Well, let's do a measurement. Okay, so let's see if I can actually run the results just to show you how to run results. Let me see if it takes too long. Well, then I'll move on to another one. I think I actually have some notebooks already made with results. There you go. So again, I took every time you want to do a measurement along the Z direction, you take these three and it gives you the answer right here. So this is what we're expecting. As you can see, nothing changed here because we're just doing a measurement. Okay. Oh, look at this nice graph right here. Is he trying to describe the situation mathematically? I guess so. Anyway, let me see if I can run. Let me see if I can run this experiment. I'll click on the side. Is it running? It's running. Okay, well, let's wait. Okay, so as you can see, there are more gates right here. All of these ones, by the way, all of these gates right here, they're all, well, all of them, with some exceptions, represent matrices. So these are arrays of numbers. So something that you should know while this thing is running. So I think it's working too hard on that. It wasn't running. So this is the up state. Okay. So you represent it like this, an up state. And the down state, you represent it like this, right? Easy, right? 1, 0 or 0, 1. And those numbers right here represent matrices, okay? For instance, H right there is a matrix that looks kind of like this, okay? This is H right here, okay? And basically, these arrays of numbers multiply with the other arrays of numbers, and well, that's a little more complicated. But I like to do it in a quantum computer because it does it for you, right? Right here, it does it theoretically, but right now, I believe it's running it. Let me see if I have a job pending here. Let me see. Pending jobs. Oh, I got 2 jobs. Oh, it's going to take 10 minutes. Well, it's going to take a little too long. Anyway, well, I guess we'll continue talking about this one. It was fun talking to you guys. And for those about to quantum, we salute you. Have a great one.